Okay, so it's basically it's named Microsoft Unpacker Engine. So the idea is to target the Microsoft MP engine, which is actually the malware protection service on Microsoft that you can download through these links. You extract it and you get some files, including the MP engine.dll, which is actually doing all the interesting stuff. So it's the Microsoft antivirus. It's a great tools with a lot of stuff in it. There are, for instance, the Tavis Ormandy already does a lot of works on it to try to find bugs and find some of them. So you can actually run the MP engine.dll on Linux and GDB it. So it's really great. Another guy, Alexei Vuladzel, have done some works on it too. You can go to its Black Hat USA talk. It's really fun to see, and it's actually a program of interest. Why? Because the PDB is available, so it's basically the symbols on Windows. So you have all the symbol. It's runnable on Linux thanks to library from Tavis Ormandy. And it's also have PDF parser, a JavaScript engine, an internal language. It's able to read .NET, VM protect code, x86, ARM. It's able to emulate them. So there are a lot of things in it, and it also have some unpackers. So the goal is, can we try to reuse the unpacking system for our own goods? So basically, if you take a look at the engine, so for instance, you have this function which is named create document object, and which is actually used when you are emulating JavaScript code. And you can see, for instance, that it's creating the document object in JavaScript, and it's setting the referrer to google.com hardcode value. So if you want to catch the antivirus, you just have to check that the referrer is these strings, and you know that you are being emulated, and so you don't have to do your stuff. So, but there are a lot of things, as I said, and the one I'm interested in is this one. When you are, when all of the packers, so there are a lot of them. If I just show you the unpack functions, you see that there are a lot of them for quite a few packers. And each of them, after having been able to depack, restore a callback that will dump the reconstruct PE file. And then a function might be called, which is named dump unpacked file. So what we want is to be able to reach this function, because if you have a look at it, inside, so there are a few tests, and then it will retrieve the unpackdir environment variable, and then it will basically dump the PE in this directory. So we just have to patch this conditional jump to always jump here. So to do that, to replace a conditional jump by a full jump, we use a 50-line code, which is basically here. So completely over-engineered. So at the end, we obtain a binary that when we run it, this is the MP client to run the code, and I'm running it on a PX file, Armadillo, old, AS protect, and a .NET emprise file. So you run it. It takes just a few seconds. It detects the first Armadillo, then the AS protect, and the .NET, and the APX is right here. So what we have at the end is the we got all of these files. You can not really see them, but for instance, if I'm opening the AS protect, so just to show you that I'm not cheating, I open the first one. The original ones is right there, but it's clearly packed. You don't have just a function and so on. But if you open the resulting file made by the Microsoft engine. You get it's as protect. Sorry, one hand it's hard. And you obtain a full PE, which is with the imports working and so on. So it clearly unpack the file. If I'm looking at the .NET one, here is for the Empress. You don't have too many things unless you want to have a look at how it works, but it's really not funny. It's .NET stuff. But after decrypting, you got the final class with the example class and all of the stuff inside. So thank you. It's just how you can reuse the MP engine to unpack for your own goods and have unpackers maintained by Microsoft.
Okay, so this is going to be very short. Since I arrived this morning, I've been dispatching a couple of blue cards around, and if you look at those, you would see that some kind of challenge on it. Some of you already solved it with a pen and paper, so awesome, thank you. For the others, if you actually want to do it on a computer, you don't have to retype everything. So there is the proper GreHack hashtag on the tweet, and then I dumped the challenge here, so you can just copy-paste from Pastebin and run it in Unicorn or Miasm or IDA or whatever. The flag is an email address, but I don't get that email, so if you solve it, just ping me on Twitter or send me an email. I would be interested to know. How many of you have seen those cards and started playing? Okay, good. Only 3 people. So the others, you have time before CTF if you're not subscribed to a workshop. Should take 10 to 30 minutes. If you spend more than 30 minutes on it, you should probably not doing it. And that's it. Thank you.
All right. Okay. Sorry. So as you will see, we are very well prepared for this RUMP, so we're going to be very synchronized, etc. So just a few words about the band, the challenge we've made for the GreHack pre-trials. First, the timeline. I think it's quite fun to see that.
So yes, we published the challenge on the 31st of August, and 23 hours later, we were already panicked because someone had reached the last challenge, which is supposed to be the hardest one, and we were even more panicked when 40 hours after he solved it.
Because it was hard for us to know if we were doing if we had the right cursor of difficulty for this last challenge. And when we saw that the first guy solved it in 12 or 15 hours, we were like, okay, it was maybe way too easy.
But it appears that after all, the second solve was like 5 days after, and the one after that was like 18 days after. So actually, I think
might be a little too difficult. The reverse timeline is also interesting. So the challenge was released at 8 p.m. on the last day of August, and we were fixing bugs the same day. I think I think it's quite common, but if you count the number of commits per day, during the summer, you don't have many activity in July. In August, it starts beginning active, and then the last 2 days, I think we didn't count, but something like 50 commits or something like
that. So yes, in our team, we have some brains who think about the architectures.
So just to be clear, we're going to talk about the first layer virtual machine, not the one you were told about in the presentation. The first one.
So the idea is that we didn't want to make a classic virtual machine, so our architectures actually reads bitcode, bitstream. Sorry. So the idea is that you get a bitstream and input, and we will decode an instruction each 2 bits. So the first instruction will be coded on the bit 0, 2, 4 extra, and the other one on 1, 3, and so on.
So if you take n bytes, you will have 2 untangled instructions in those 10 bytes.
Yes, and once our decoder, which is called scatcat, decode it, it sends it to 2 other processes that are going to execute the instruction. So, for instance, you can have 2 add, which are going to be executed at the same time.
Except if there is a dependency between the first instruction and the second one, in which case the assembler that we've written for our bytecode is adding NUPs between instructions that are interdependent. So it's obviously for performance reasons that we do this.
Yes.
Very fast. And everything. Every rectangle is one process, and they're communicating through, as it was told, through thinnules and through there is the shared memory. There are some pipes, etc.
So yes, the first one we call the band, which has 3 sub-processes, actually is run once to interpret the VM with left-right, which was described earlier, and then there is also one which decodes it, and so there are multiples of the band started, which makes a lot of processes.
Yeah. A few words about flag unicity, because it's a huge problem that we don't want some guys to find flags that are not accepted by the platform. So we put a lot of thought to this too. But we want to thank Nicolas, because he solved it for us actually. He sent us an email when he found solutions. Like, I have plenty of solutions that make sense, but they are not accepted. Here is my file with all my solutions, and we have like, I don't know, 50 solutions or something like that. So we added them all in the platform, and then they were all accepted. So for the next guys, it was okay to flag with one of those. So thank you.
So obviously, in our team we have so the assembly we made for this virtual machine is called I/O, and obviously our developers need assemblers and tools to build program in I/O. So it was designed by reverse engineers for reverse engineers, and we are going to describe some features. And the first one is we have a very great instruction set, which is composed of like 12 instructions or so. Yes. So with all these 12 instructions, we managed to do everything: read the user input, allocate memory, and so on.
So yeah. We wanted to have, well, for instance, if you take a look carefully, you might wonder how we can do a subtraction of something like that. So we don't have those kind of operations. We just have an add and an egg, and this allows to do every subtraction. And there's the same for instance, you only have one jump, but you still can do conditional jumps.
So yes, one feature we did for our developers is that when you want to jump in another function, you just basically call the jump instruction and set the label you want to go to. But in this case, our developer was like stuck, and he didn't understand why the jump instruction was failing.
So first, the jump takes 3 operands. I think it's important. Because the first one, so when you have a jump instruction, it will look at the value of a specific register, and if it's 0, it will jump to the first target. If it's greater than 0, the second, and less than 0, the third. Something like that. So that's how we have one instruction for all the conditional jumps.
Yes, and since those are immediates, they are coded on 9 bits, because why not? And with a signed bit, so it makes 8 bits, which is 256 bytes into our bytecode. So we can only jump 2 plus 256 or minus 256. And when you want to reach a far function, you actually have to put a middle jump and jump to this jump, which jump to the other location, because you can't reach it from once.
So why? Because when when we designed the I/O instruction set, we didn't think that we would end up with large I/O programs and then we would not be able to jump wherever we wanted. So we fixed it like this with an intermodule jump.
And since we are in 2018 and we are great developers, we did this with test-driven development. And as you can see, this is our test suite at the end of the challenge. So we just do make tests, and it prints red and green stuff, and that's good, it works. So that's it.
So actually, what this shows is that we have a lot of tests, but at the very end, in the last 2 days, we did not care about the tests anymore, so we break everything to go straight to the point.
And there's obviously a lot more, but if you want to see all of this, we will open source the code, so you can see what we did. But we only had 30 minutes to prepare the slides, so thanks for your attention.